Okay, so welcome to the second live session. We have a few participants here. Okay, so this time we'll cover data splitting and cross-validation and what kind of cross-validation is efficient, and we'll go into the types of cross-validation and the regression. The regression, that's very important and fundamentals of machine learning. We'll go into linear regression and variation of linear regression. So maybe like ridge regression, lasso, kind of that. And then the classification. So in the classification, we'll go through logistic regression and decision tree. And then finally, we'll sum all it up in the Boston house price prediction task. Okay, so let's go first with common, with data splitting and cross-validation.
Sure. All right, let me see. I have the notebook open, so it will take me a second. Share screen. This one. All right, let's see.
Yes.
Cool. All right. So this notebook introduces sklearn. sklearn is a very, very useful framework that you can use to do all sorts of standard machine learning things. It's not as useful for like deep neural networks and things like that, but all the classical machine learning approaches that we've been looking and we'll be looking over the next session as well, you should be able to find in sklearn. All right, so let's talk about training and splitting. What's the idea behind it? So hopefully, if you've had a look at the notebook, you should be able to have a good guess by now. But in general, in machine learning, we want to use some data to learn some properties of this data in order to be able to predict something down the line. Now, we often have access to just limited data, not unlimited data, and we want to train on that data. The idea there is that if we use all the data that we have for training and use the same data to make predictions, we're sort of cheating by already like knowing something about the test data. For example, in linear regression, which we'll take a look at down the line, we'll often have access to both input data and like regression targets. For example, if I want to learn, I think in the lecture we gave the example like the weight of apples. In my training data, I already have the weight of an apple. So if I later down the line use that data to test on it, I'll be able to make a very good guess of what the weight of an apple should be, because I've already seen that particular apple. So the idea of splitting a data set into the training part and a test part is to leave the test part out of all my considerations for the model, such that you have something to use as like a last benchmark and see how well my model generalizes to new previously unseen data. So how can we do the split in sklearn? So we have to fill in some things here. I can just well, the solutions here, so I can just copy paste things in, just a bit faster.
Yeah, and because last time you were running out of time, so this time we were copy and pasting solutions instead of typing it.
All right, so here we're asked to fill in, to create a data frame based on the data that we have. And the way we do it is just by giving the appropriate variables, which is the data frame and the columns that we want to name, the names of the columns that we want to assign to the names of, English is hard, the name of each column we want to assign. And then we want to also add our targets into this data frame, just for the purpose of being able to see everything at once. So you should have been able to pass through this fairly quickly. I missed something, the F. So I just used that here, and I'm able to get a view of the data that I'm going to be using. We're going to be using the iris dataset that you should have, that you will see in these notebooks at several times. It contains data about features of different flowers or plants, I forget, such as the length and width of leaves and like petals, if I'm not mistaken. And yeah, so you should be able to create a dataset fairly easy here, where you have these different columns describing each of the features, as well as the class of each of the flowers that we have. Cool. So this is just creating the whole dataset. Now we want to split our dataset into a train and a test section. And the way we can do that is by using the train test split function from sklearn and giving it different parameters. So the train and test splitting that we do in this visualization looks like I'm just going to take the first part for training and the last part for testing. But you can, in general, do whatever you want. You can, take like examples 1 and 2 for training, and then 3 for testing, and like take every third example for testing or something like that. There are some situations in which doing something like taking only the last part of the data has a meaning, but in this particular case, we can do whatever. We can just take random samples for testing, and the way we can do that is by changing the random state, such that we can get different samples. We use the test size parameter to say how much of the dataset as a fraction we use for testing. So here we're asked to visualize or print out it's going to take some statistics of these datasets. So just copy paste typing. The missing buckets somewhere. These buckets. These probably was not in buckets. There you go. What do you want? All right, let me just copy this thing. Waste time. No. There we go. So we wanted to split it such that 70% of our data is obtaining, 30% is for testing, which is exactly what we do here.
There is a typo for the percentage symbol.
Oh yeah, sorry. Yeah, so they should be times 100, obviously. Oops, what did I do? There we go. Now it's correct. All right, so next we can do some visualization of what we've taken, what we've allocated for each of the different sets. You'll notice that in our data set, the first 40-something things were all of the first class, the second were of the second class, and the third were of the third class. Now, in this situation, it wouldn't have made sense to make the split of using the first 70% of the data for training and the last 30% for testing, because we would never observe data points with iris class tree, like this brown class. So shuffling in general can be quite an easy way to avoid a mistake where like you don't observe a particular data with particular features just because you don't know what the data is like. Like you haven't done the exploratory data analysis well enough, and you've missed out on something. So shuffling good in most cases, unless you know for sure that you need to preserve the order of the data. Cool. All right. So next, we want to do some manual data splitting, which this is mostly like there's no one correct answer here. You can go about it several different ways. What we do here is we're going to get some random indices for the tests, and we're going to say that train is all that's left. Right? So we continuously sample without replacement test examples, and then leave the train examples. Here again, just want to visualize. Stuff. Let's do that again. But do something maybe. There we go. Let's say I want 0.2 this time. Yeah. So we're able to using this code split our data into two sets. We can do this again. See that we do take things at random from our test set, and that's on how the splitting is performed. Let's talk about cross-validation now. Cross-validation is quite useful technique in general. So the idea is the following. Even though I'm taking random samples from my data set here, if I'm unlucky enough, I may make wrong conclusions based on the test set that I've sampled here. So in order to be that extra bit robust, I can perform this operation several times, taking different samples from the data. Now, I'd like to avoid picking the same sample for the test data multiple times. So what I'm actually going to do is I'm going to split my data set into different groups called folds. In the example here, what is this? Like, I think it's 10. We split our data set into 10 folds, and we do the following. We use all but one of the folds for training, and we use the remaining fold for testing. And we do this repeatedly for each of the folds being the test fold, and that produces different characteristics of the model. So if you average the error that our model incurs at each of these different iterations, we get a much more robust estimate of what our error will be on new unseen training data. This is mostly about like statistical robustness. You can sort of imagine if I throw a coin, like once, I would get either heads or tails, but if I throw it like 100 times, I should get about 50 heads, about 50 tails. So obviously having more done the same thing more times gives me a better idea of what the statistical properties of that thing is. So how do we do k-fold cross validation? Well, luckily sklearn can do that for us. So let's see. How many splits do we want? So I think we're told here to do 4 splits. We have some Hilbert functions, and we're going to do k-fold splitting here. So let's look at the code if there's anything interesting. So k-fold allows us to define some properties. I think that actually comes in next. All right, sorry. So k-fold by default does not do the shuffling that I was talking before, and you can see here that it just takes the first 20 or whatever it is symbols for the first fold, then takes the next things and the next things. That's useful to know in case you need to be worried about shuffling. As you can see, the last things are unshuffled here as well. So it's again useful to keep that in mind when you're operating with these things. Are there any parameters of interest here? Let's see, what's the fold? It's plotting. See. All right, so sorry. There are different cross-validation techniques that you can play around with, and you can read up more about them, I think, in this Medium block right here. What I talked about so far was cross-validation with k-fold. You can play around with these different things using the visualization that we've provided to sort of see how these the different splits happen, the different techniques, what kind of split they do. Finally, in this notebook, you're asked to do k-fold by yourself, which again, there's no single solution to this. The solution that we provide is very similar to the shuffle sampling that we talked about before, with the exception that this time we don't take things at random, but take subsegments, sort of like as you saw here, just segments of the data of appropriate size. So that should let's see. Oh, here's another one. I'll do this for 5 things, and there we go. So this code does in fact do the k-fold splitting. So that covers the notebook on data splitting and cross-validation. Are there any questions about it?
I think comments because I don't know why there is a fault, but I think we can show the solution and we can see the differences between different technique of cross-validation. Yeah, I can. So can I share my screen to share it?
Of course.
Yeah. Thank you. Yeah, because this notebook is made by me, so I may be more familiar with it. So can you see this screen? Yeah, just a very clear, very quick going through. The k-fold, that means we just simply cut like the diagram shows. We take different segment of the all data. But the clarified k-fold means that we take the samples, the number of samples according to the cases in each class. That means we make the k-fold more balanced in the meaning of number of classes. So that is obviously better than the k-fold, simple k-fold. And we also have some similar techniques. For example, we use the shuffle split. That means we didn't care about the number of cases in each class, but we shuffle the place that we take the case here. So that means we can send. That's also better than the simple k-fold, right? And or we also can combine the shuffle and with the stratified two strategy together, and we can get a better and also random sampling from this technique. So that is a demonstration, and you can run it to see. Okay, we will release the solution later on. So that's what I want to supplement to what Cameron discussed with you.
Thank you, Nick. Yeah, that was very useful. Sorry, I missed that. Cool. So I think, yeah, if there are no other questions about this notebook, we can move on to this one.
Yeah, thank you, Nick. So next one is regression, right? So Angelo. Yeah.
Share my screen real quick. Okay. So, all right. So I hope you guys enjoyed this notebook. This is linear regression is a very important part in machine learning. And so what we're trying to do is in this notebook is gonna first import all of the libraries, and we're gonna create a random data set. So just X and Y. And the dimensions of this are just gonna be 100, and they're gonna be column vectors. So first let's try to plot it, and I'm just gonna do normal scatter plot. So yeah. I'm just gonna name it X and Y. So yeah, we just created a random data set, and the first step is to create a method such that it gives off a prediction based on the slope, the intercept, and the X values. So remember, we chose just a random range of X values. Let me do that. And yep. So what we're going to return is just a simple linear formula. So X times A, we're going to transpose this since X is a column vector, and then add the intercept. So yeah, we have the prediction equation. That's going to be our predictor. And step 2 is we're going to calculate the difference between the predictions and the actual Y values in our data set. So the first thing we have here is the learning rate. We're going to get to this in a second. And so we have to calculate some sort of error between the our actual model and the data. So we're just going to return an error, and this error is just going to be Y minus the prediction function with inputs A, B, and X. All right, so this is just going to give us residuals. All right, so to update, so our model bases off the principle that we're going to start with our slope and intercept being equal to 0. You can see here. And we're going to update these values based on mean squared regression. So we have our mean squared error, rather. So we have our error right here. We can define mean squared regression real quick. So it's just, let's write down the equation. Yeah. So it's just going to be the sum through I of the error, right? I'm just going to do hat, oops, hat Y, subscript I, minus the predictor, which is just going to be Y I. See this, and we're going to square this. Yep. And basically, this is going to be our mean squared error. And this takes the some shape of a parabola. I'll draw it real quick here. And so, oops, sorry about that. So basically, not bad. We're going to have a real value for, let's say, the slope, m. And we're going to have a cost function that's going to be parabolic. And based on the derivative at each point on this, we're gonna tell it how much it's gonna move towards the value. And this is gonna be proportional to this learning rate. So we don't want the learning rate to be too high, such that it oscillates too much. And we just want it right so it's precise and fast. So as you can see, this is the change. We're going to update delta, the slope by, if you can see, this is, well, actually, sorry about this. This is just divided by the number of variables. And so as you can see, this is the derivative of this. And we're going to update it proportional to its derivative, negative to that, because we're going to go to the opposite direction, proportional to the learning rate. We're going to update these values and apply it to the gradient descent. So we're going to actually descend. We're going to actually update our function continuously, our model continuously rather. And so we just plug in the error. And for our changes in the updates in the slope and intercept, we are gonna update AB. All right, so yeah, so we made our gradient descent, our gradient descent method. Now we're gonna test it. And so we're gonna loop through different epochs of this model. So first we're gonna loop through 10, 100, 500, 1,000, 10,000. Okay, and line B. Yeah, so this is gonna be just the gradient descent.
I think when you update AB, you don't have iteration parameter.
Oh, right, sorry.
Yeah.
What about that?
It's fine, it's fine.
And
Yeah. I
just
think
this,
the rest of it.
this is the learning rate, right? Sorry.
Yeah.
All right, and gradient descent. So yeah, we're just gonna update this. Yeah, here's the iteration. And let's see. Second iterations.
I think there's a spelling mistake in calculate error. Can you compare it to the name of the function? Yeah, so the actual function is called calculate. Yeah, there's a error there.
Okay, thank you. So let's just do this. And yep. So as you can see, we start with an intercept of 0 and a gradient of 0. And then as the model trains and descends the cost function, we are going to approach the true regression line asymptotically. Okay. So now we are going to attempt linear regression with sklearn, scikit-learn. And okay, so now we're just going to create another model, a model in scikit-learn. It's going to be a linear regression model. And we're going to fit it with X and Y. And we're gonna extract the predictor. Now we can see the results. All right. So yeah, this is just a built-in model in scikit-learn. And yeah, we can also add features to our data set. So we can improve basically the more parameters, the better. So we're gonna import the CSV file, which is advertisement data from Facebook, Instagram, and Twitter. And yep. So I'm just gonna import this CSV file. And as you can see, that it's 200 rows, 3 columns, and then a label, which is gonna be the last column, with the sales information. So our model is going to be another linear model. Fit our model and predict. So, okay, so now we have the coefficients of, basically it's going to be a superposition of all the features in the data set, and in a linear, basically a linear combination, and each placeholder basically has a coefficient. So we define this as model the coefficients. First coefficient, which is going to be for Facebook. First 3 are just going to be Facebook, Instagram, and Twitter. First 3 columns. The last one is going to be the intercept. So as you can see, these are the different coefficients. And now we're going to predict the expected values. So using our predictor and our linear regression model, we're going to return the sales with these given initial conditions. So 100, 200, 0 respectively for Facebook, Instagram, Twitter. And the expected sales are 45. All right, so linear regression for polynomials, it's a bit different. Take it. So we're going to create a polynomial feature instead of a, well, actually, we're going to create a polynomial feature. And transform the data such that instead of having a linear combination of all the possible features, we have a linear combination of all possible combinations of placeholders. So if you have, this is a good example, if you have 2 features, you're going to have either just a constant, a single feature, first feature, second feature, first squared, and then a combination of both, such that the maximum degree is 2 in this case. So we're going to implement that here. Yeah. X and this. Okay. It's going to return the shape of the polynomial features. Now we're going to create another linear model. Linear regressions, rather. Right. Should work. Oop, yep, forgot to fit. And we fit our data into here. So our poly X. Oh, yeah.
I think it's the last line. You should fit the with label.
Oh, yeah, sorry. two values for a fit. And so yeah, we have a poly shape. Instead of 3 features, we're gonna have 10, right? There's gonna be 9 plus a constant. And we're gonna try to predict our label from that. Yeah, okay. Now to plot them, we're gonna use a basically a train split, train test method of validation that Cameron explained before, and so we're gonna split this. Split this data set with size 20%. And so basically, yeah, we're gonna select at random an 80-20 splits between training data and testing data from the data set, both for the X values and Y values. And yeah, so like the train, these two initialized arrays will be the respective errors. And so yeah, and we're gonna loop until we're gonna loop from 1 to the length of the actual training set, which is a subset of the whole data, and predict the well, fit the model with the training data until so we're gonna start with 1 until the length of the train, and hopefully it's gonna get better as the data set increases. We're gonna use this as a predictor and predict the validation set. So use the validation set. And so to get the train error, we imported mean squared error. The training error is going to be between training data indexed and the prediction of the training data. Next, we are gonna calculate the error of the validation. Let's see, and that's gonna be validation value and the predicted value. So I'm going to plot it and plot here. So yeah, as you can see, well, since we started with only 1 data point in the training data, the error is very high in the test and very low in the training data set because there's only 1 value. And then as the epochs progress, you can see it asymptotically, which is 1 mutual value for the loss. So I think Danny can take over from here.
Yeah. So yeah, thank you very much, Angelo. And while Angelo was explaining, I wrote some mathematical equation on the paper because I saw Angelo was doing some drawing thing, so I thought it was a great idea. So let me share my screen. So on top of wonderful Angelo's explanation, I'll explain some more. Okay. So do you see this?
Yep.
So let's say we're doing y equal to mx plus c. And then the loss function, we're doing OLS, right? Ordinary list squared. The loss function of that would look like this. So we are getting the error and square it and sum it and then divide it by n, which is the average. And then we do derivative. So we derive e, with respect to m. So that would be this, using the chain rule right here. And then that one, let me, so this is the solution of the regression. So you see this one, delta A and delta B, right? So delta A and delta B thing here represent this. So delta A will be this one, and delta B will be this one, the derivative for bias, right? So that's why we had this one. And then we are updating delta A, updating A and B by minusing it, because as you could see from the Angelos graph, if A position was on the right side of the graph, this graph, the gradient should be the plus. So you have to minus the plus to move that point to the left, right? And vice versa. So that's why we were minus in the upgrade. So let's go to the other regression models. So here we have ridge, lasso, and elastic net. So the idea here is that even linear regression can overfit. So we're trying to add some regularization on the linear regression. So ridge regression is using L2 regularization, and lasso is using L1, and elastic net is using both L1 and L2 regularization. Okay. So for example, I wrote another equation. So here you see we normally upgrade our gradient like this. So weight, so the next weight is current weight minus learning rate times the gradient, right? Here in the ridge regression, we're going to add this bit. This is the regular, in this term, the final upgrade, gradient upgrade would look like this, which means if you look at the red part, at each iteration, you are decaying the weight. So this is the ridge regression can be called as a weight decay as well. So yep, that was different kind of regression, linear regression. So if you look at it, ridge and lasso looks quite same in performance, but if the data gets larger and larger, it will look quite a bit different. And the last thing that's using both ridge and lasso regularization term. Okay, let's go on to the classification. Since we don't have that much time, in the classification, I am going to look at the logistic regression for just logistic regression.
Sorry,
okay.
Danny. Sorry for breaking you.
Yeah.
One thing that I want to add is that what we upload the pre-recorded video contains a detailed explanation for the gradient descent, and you can check that if you wish.
Yeah. Thank you very much. Okay, so the classification. So the basic idea of classification is, what if we have this kind of data? If the data looks like this, can linear regression perform well? Well, if you can draw a line like this, but that underperforms, that's not really good one. So we need a different one. So that's why we're doing a logistic regression. All right. So this graph compares logistic regression and linear regression. So as I said before, this is why we're using logistic regression. Let's implement a logistic classifier from scratch. Okay, so we have the data, and this is our cost function. So if you have studied logistic regression before this notebook, you will be familiar with this mathematical equation, I guess. So this is called cross entropy loss. So as you could see from this red graph here, this is a sigmoid function. So what we're trying to do in the cross entropy loss right here, if you look at it, this is the probability that we predict y as 1, given that given x, and then this 1 minus probability of that would be the same as the probability that we predict y equal to 0, given x. So what if the real y, the yi here, what if the yi is 1 in the label? It means that if you plug 1 into this equation, the rightmost part, it will go to 0. And we end up minimizing minus log of this probability. Okay, and if y was 0, this term will go 0. So we end up minimizing minus log probability of this term. So that's the intuitive of this loss function. Okay. Let me actually, because we don't have that much time. Right. So this was the implementation. So if you see the sigmoid function right here, it's just the 1 over 1 plus mp dot exponential of minus z. Minus z here equals to minus theta x, which is our weight and input value. And then the loss, we have the loss right here, which is exactly the same, the cross entropy loss. I used mean because you're calculating a mean right here, right? Okay, and here you do logistic regression parameter estimation. So what you had to do was this, right? Update the parameter with the gradient, and the gradient was this one. I just gave it to you guys, but if you do calculation, you'll definitely get it. And then if the sigmoid, if the final output was the probability, right? The final output is the probability from 0 to 1. If the probability was bigger than 0.5, you do append the prediction. And then if it was less than 0.5, you put 0. So exactly this. If it's bigger than 0.5, you put 1. If it's not, you put 0. And that was the implementation. So we trained it from the Irish data set, and from the logistic regression, we got the accuracy of 66%. I mean, the F1 score was 66%. Okay, decision tree, this was just an optional part for you to guys practice some part of tree. So this is how to implement tree with node with breadth search algorithm, but this was totally optional on this one as well. So let's do this exercise. We're doing a digit classifier. So if you can visualize it, so this was the code I wrote. So what this code does is, after this, you have to print it out. So this code is just printing out the label and the matrix description, the matrix show library of that matrix. So 0, 1, and 7. So here we're going to use decision trees classifier, and then we're going to use k-fold cross-validation. You have experience with common, right? So here, what we are trying to do is, so you first split with train ratio, train 7 and test 3, and then you split X train. You're not splitting other thing, you're splitting X train with validation set of train and validation, and you're getting the index of it. And since you got the index of the train and validation set, you are getting another train and validation set, which is specifying the index right here. And then you're doing a grid search CV. So grid search CV is you have different set of hyperparameters, and then you're doing a cross product of those hyperparameters. So if you have 2 and 3 candidates, you're doing cross product. So you're explaining with 6 hyperparameters, and you can choose the best one among those 6 candidates. Okay. So yeah, we've trained it, and then we'll try to extract the best one. So how do you extract the best one? You can extract the best one by having a best param attribute. So in grid search CV function, you have an attribute called best params and best score. So you literally get best parameter combination and best score. So the combination was the depth of the tree was 15 and the minimum sample split was 2. So from that, you could get the best score of 82%. Any other questions? Okay. If not, we can go to Boston house price prediction. All right, so let's do some EDA. I'm sorry, give me a second. Okay, so we're gonna plot the graph. So we have in the Boston data set, to know what we have in the data set, we're just gonna do some data analysis, I guess. So let's see. So this is what we have. Yeah, we need to do another thing. Okay. What is the problem? Okay, let's just, I'll bring up the solution file here. We are running out of time. So what we have here is this. In the features, for the features, we have loads of features that describe the house. And if you look at it using the Seaborn, and in the Seaborn, actually you have the reg plots, which plots the linear regression line automatically. So if you plot it, you get these data points and linear regression lines. So if you can see some of it, like L, stat, or RM, those kind of thing can be done in linear regression, I guess. But if you look at these features, those are quite messy, right? So if you look at the correlation matrix, so correlation matrix, you use Pearson correlation, if you know. So it's correlation coefficient. It's a range from -1 to 1. And if it's close to 1, it means that it's 100% exactly the same. And if it's -1, it's definitely it's just the opposite. So if you see the diagonal here, it's of course 1 because you're comparing the same features. So if you input the correlation matrix into the Seaborn heat map library, you can visualize the heat map as well. So let's predict with linear regression. So you know how to do linear regression. Just import linear regression from scikit-learn library, and then you train it by fit and predict, and then you do mean squared error, right? And then if you do input square roots of the linear regression MSE, you will get the RMSE, which is quite often used in machine learning evaluation evaluation metric. So, yep, the result of the linear regression was not that bad. So what I plotted here is in the y-axis, I did a predicted price, which is y hat, and then on the x-axis I put the y, the true y, expected price. So if the data points looks very similar to the y equal to x shape, it means that you got it quite well. Okay, so we have decision tree based algorithm here, which is gradient boosting. So gradient boosting, you make a lot of weak learners, and then you enhance that model by just improve that model by combining a lot of weak learners at the same time. I mean, when you go through the epochs. So that's XGBoost, one part of the gradient boosting algorithm. So we, as a model, we're going to try ridge, lasso, elastic net. We did before, right? And the gradient boosting, simple gradient boosting algorithm, and stochastic gradient descent regressor, and then XGBoost regressor. So this is the dictionary. So if you loop through models.items in the name, you will get the red part, the names, and the model, you will get actual model. So if you fit it, and then I'm gonna put prediction with the name in the pred record dictionary. So if you call pred record name, you'll get the prediction, okay? So let's look at the performance of stochastic gradient descent regressor. This is very, very messy. It doesn't look like a y equal to x, so we're not going to use that. This is actually how you select your models when you're doing machine learning projects. You try out different models with accuracy and plotted, and then you pick the best one. XGBoost, this is quite fair, but it doesn't look like a best one. I think gradient boosting was the best one among these model candidates. Okay, so this was a very simple solution of Boston house price prediction. If you go to Kaggle or if you Google it and find a wonderful blog, there's way much better solutions out there. So you should definitely go check it out. And we don't have to do this part, but there's a small taster session for neural networks. So if you know neural network, if you know what neural network is, you will definitely understand this neural network function. So I'm using carrots for the simplicity. I'm adding 512 because the input so that's the first layer of the neuron, and the input dimension is of course the dimension of the Boston data set. And then the data will go through dense layer, activation layer, and dense layer, activation layer, and so on. And finally, we have, in the last layer, we have dense 1, because we want to predict one thing, not many things. So yeah, neural networks performance was like this. It's very great, right? So it's not that every time neural net performs better than every algorithm and every classical ML algorithm, but I think most of the time, neural networks, if you have good parameters and good hyperparameters, it will beat most of ML algorithms. So we will look into neural networks in the next session. So stay tuned. And that was it, I guess. Any questions? Nope.
If you guys need time to digest what's happened or want to watch the recording later, you can always ask in the Discord channel as well. We're always happy to help there.
Mm-hmm.
And
Discord channel is always open.
Yeah. And we will also record, we're planning to record a further video to explain some of the classic models in traditional machine learning. And because I think most of you may be curious about how, what's the principle, what's the backend logic of the models. So we will try to make that video to explain.
Yes. So remember, always, as always, Discord channel is open. If you go to our Discord channel, there's a separate channel called ML Tutorials question. You can ask all of the questions right there. Right, any feedbacks or anything? Otherwise, we can let you go.
I think you can stop the recording for sure.
Oh, yeah, sure.